It's really important that you know the TCP IP model for the real world. You'll often hear network engineers saying there's a problem at layer 1, or perhaps there's an issue at layer 3, or there's a problem at layer 7. What does that actually mean? You need to learn the TCP IP model and be aware of the OSI model. Now, why do we have these models? This problem, unfortunately, still exists today. Here I've got a Pixel phone, Samsung phone, and an iPhone. One of the reasons the OSI model was developed was standardization. In this example, Pixel phone supports USB-C, so I could plug that cable in. Samsung phone supports USB-C. But this is an older iPhone. It only supports a lightning cable. So this cable is proprietary, can't be used with these devices. This problem used to also exist in networking, where vendors would create their own proprietary systems, own proprietary protocols. And the OSI model allows us to stop vendors making proprietary protocols that don't work with one another. And one of the ideas with the OSI model, or Open Systems Interconnection Model, created by the International Organization for Standardization, or ISO, was interoperability, standardization of interfaces, standardization of protocols. Fortunately, more modern example, later versions of Apple iPhones have to support USB-C. So now we can take the same cable and use it across different vendor devices, rather than having to use a proprietary cable for every vendor device. Now, in the same way, in networking, we have standard interfaces. Now, this is an RJ45 connector. Technically, it's got a different name, but in the real world, people refer to this as an RJ45 connector. This is a Cat5e UTP cable, unshielded twisted pair cable. I'll talk more about cabling in a separate video, but what I want you to realize is this cable can connect to a Cisco switch like that. I could connect it to a Unify switch. So Unify switch, Cisco switch. In the same way, same cable could be used with a Netgear switch, or same cable could be used with a TP-Link router. Because of standardization, this is a standard interface that can be used across multiple vendors. In the old days, we used to have proprietary protocols, proprietary vendor implementations. That meant that if you're, for instance, using a system from one vendor, and you wanted to support another vendor, you ended up with two separate networks. Fortunately, today we don't have that problem. In today's world, we use TCP IP, which means that the protocols or languages that we use on the internet are supported across vendor devices. Cabling is standardized. Protocols such as TCP or UDP or OSPF are standardized across vendor devices, gives us interoperability between different vendors. You don't have to worry about buying a specific type of Ethernet cable like you had to do with lightning cables from Apple as an example. I mean, on the other side of this cable, we have USB-A, here's USB-C. These are standard interfaces. Fortunately, the EU have forced Apple to move from lightning to USB-C. In the same way, with the OSI model and TCP IP model, we have standard protocols that are supported by multiple vendors. In the TCP IP model, we have what are called RFCs, or request for comments, that specify a protocol, such as TCP. Notice how old it is. Protocols do get updated, so you'll see various changes to protocols. But notice, as an example, I could just search for a protocol such as OSPF RFC, and here is OSPF version 2. RFC is this. Notice how old this one is, 1998. So when we get into the nitty-gritty of the TCP IP model, OSI model, don't lose sight of the reason why this was created. In the past, we had proprietary protocols. Nightmare from a consumer point of view. Great from a vendor point of view, because they control it, they get all the money. We could make some really snarky comments about Apple as an example. The ISO allows for multi-vendor software and a layered approach for interoperability between devices. The idea here is that we split responsibilities. Some people are responsible for certain parts of the network. Other people are responsible for other parts of the network. So as an example, you as a network engineer may work with these kind of cables, but you don't physically create the cables, you just order them in. And you know it's going to be standardized when it arrives. You're not going to create your own fiber cables. You could do that. You could create your own routers. You could create your own switches. But generally, what we do is we split the responsibilities, where someone focuses on creating cables, someone focuses on, for instance, creating routers. Some of us are focused on configuring those devices. Some of us are focused on writing applications that use a network, but we don't understand how networks route traffic from one device to another, as an example. So this is what the OSI model looks like. We have 7 layers starting at 1 going to 7, and their names are all people sleeping through, networking don't pass. Now, that's obviously not what the layers are called, but hopefully that helps you remember the various layers. Here are the actual layers. At layer 1, we have the physical layer. At layer 2, the data link layer. Layer 3, network layer. Layer 4, transport layer. Then session at 5, presentation at 6, and application at 7. Now, I won't bore you going through all the reasons again for the OSI model, but the whole idea is to have standardization and interoperability between different vendors and technologies. Now, I'll be talking about the different layers in more detail in a moment, but life isn't as simple as this. Unfortunately, it gets a bit more complicated. In the past, we had competing organizations with different models. We had the OSI model and the TCP IP model. In the real world today, we use TCP IP. The protocols that we use today are IPv4 and IPv6, and I'll explain where those fit in the TCP IP model in a moment. But in the past, there were different protocols. We had protocols such as NetBEUI or IPX, other types of protocols. So it wasn't always clear-cut which protocol would win. Would IPX win or would TCP IP win? Today, fortunately, we just have to focus on TCP IP version 4, version 6. So this is what you need to know. In previous versions of the CCNA course, they taught the OSI model. There was a lot of debate about how practical this model was in the TCP IP implementation that we use these days. The original TCP IP model had 4 layers. So we only had link layer, internet layer, transport layer, and application layer. Only 4 layers. However, in the CCNA and in the real world, we use the hybrid TCP IP model. This is a 5-layer TCP IP model, which consists of the physical layer at layer 1. Notice how that's similar to the OSI model. We have the data link layer at layer 2, similar to the OSI model. And then we have the network layer at layer 3, similar to the OSI model again. Transport layer, similar to TCP IP and OSI model. And then we have the application layer at layer 5. So rather than just 4 layers, we have 2 layers. The link layer in the TCP IP model is split into 2, data link and physical, similar to the OSI model. Now, the one that you need to know for the real world is the 5-layer TCP IP model. Wikipedia shows the different models available out there. So just be aware that ARPANET is how the internet was started. We had 3 layers, application, host-to-host, and network interface. And then we had RFC 1122 with 4 layers. And then there are various 5-layer models as shown here. The one that's most famous is application, transport, network, data link, and physical. And then we have the 7 layers: application, presentation, session, transport, network, data link, and physical. Now, don't get lost in the details. There are 3 layers. The most important one to know is the 5-layer TCP IP model. That's actually what we use in the real world. I'll show you using Wireshark how it actually looks on a network. Now, that can be a bit scary the first time you see it. So don't worry too much if you don't understand the Wireshark captures right now as I show it to you in this video. But you'll learn this as we go through the course. You need to know your layers. You need to understand the protocols used in networks. So we're going to focus on the TCP IP model, where we have application, transport, network, data link, and physical layers. The 3 OSI layers are combined into a single application layer. But, and this is where it might get confusing in the real world, we still often refer to this as layer 7. So in the real world, network engineers will talk about this being a layer 7, as in there's a layer 7 problem. In other words, a problem at the application layer, even though we only have 5 layers in the TCP IP model, or 4 layers in the original TCP IP model. That comes from the fact that this is layer 7 in the OSI model. Now, don't get hung up about all the different types of models. What you need to know for the exam is the 5-layer TCP IP model, and you need to know which protocols and which devices are used at which layers. You'll see references in books and documentation to the OSI model, as well as the original RFC 1122 TCP IP model. But for the exam, you need to know this hybrid or 5-layer TCP IP model. That's the one that we're going to focus on from now on. Now, one of the ideas with the OSI model and TCP IP model is to put protocols at certain layers. So as an example, we would have IP version 4, IP version 6 at layer 3 in the TCP IP model, TCP UDP at layer 4, Ethernet, PPP, HDLC, which are encapsulations on various technologies at layer 2, and then we'd have the physical media that we're sending traffic across, which could be Ethernet, Wi-Fi. So as an example, a fiber cable or a copper cable at layer 1. And then at layer 7, we would have protocols such as HTTP, HTTPS, Telnet, FTP, TFTP, a whole bunch of protocols. Now again, a protocol is just a set of conventions on how we communicate. So as an example, if we're using HTTP, we need to agree on the conventions of HTTP. How does the protocol actually work? Again, in English, we have certain conventions which are different to, say, other languages. So the idea here is we try and put various protocols into certain layers. But for the real world, just be aware that it doesn't always work as nicely as this. So don't get stuck or hung up on trying to put every protocol into a specific layer. Some people get into fights about this protocol doesn't reside at this layer, it resides at a different layer. Don't get too hung up about that. Don't get stuck into trying to fit everything neatly into a model like this. So as an example, a model for a house is just that, it's a model. It's not going to be exactly the same as the physical implementation, the actual house of the model. So there will be variations. Application developers may decide not to follow the rules or the conventions and put their protocols in weird places. But for the exam and for CCNA, in your mind, we are going to try and put most protocols at specific layers, and that's what you're going to learn. We're also going to be putting devices at specific layers. So as an example, a hub at layer 1, switch or bridge at layer 2, route at layer 3, TCP, UDP again at layer 4, and our layer 7 protocols here. But before I explain that in more detail and show you with physical devices, let's have a look at what each layer does, because you're probably wondering, what is layer 1 about, layer 2 about, layer 3 about, etc. So physical layer is probably the easiest one to understand. That's the layer that transmits raw bit streams as electrical, optical, or radio signals over physical media such as cables or wireless. So here's an example. I have a fiber optic cable. Notice the light. Single mode fiber optic. That's different to, say, multi-mode fiber optic. So notice how the pattern is different in multi-mode fiber versus single mode fiber. This is like a solid pattern, and this has a dispersed pattern. But notice in that definition, we are sending bit streams, in other words, data, across an optical cable as light. That's different, once again, to a copper Ethernet cable that uses electrical signals. So electrical signals are sent through copper cables. As an example, light traverses through the cable, allowing communication from one end of the cable to the other, or in this example, electrical signals are sent by the transmitting party and then are received on the other side. That's how devices communicate. That again is very different to, say, Wi-Fi. The standards for Wi-Fi are going to be very different to optical. That again is going to be different to, say, satellite. So here's my Starlink satellite dish. So Starlink's transmission to satellites is going to be different to, say, 5G. So the physical implementation of how data is transmitted on 5G is different to Wi-Fi. It's going to be different to copper. It's going to be different to fiber. It's going to be different to satellite communication. But the idea is that we're sending data. In other words, we are sending bits from one party to the other through some kind of media. Now, the data link layer, layer 2, manages physical addressing or MAC addresses, framing and error correction between directly connected devices. Notice the keyword, directly connected devices. The reason for that is there are different encapsulations and different ways that things work at layer 2. So as an example, it says MAC address there, but not all implementations use MAC addresses. Here I've got an Ethernet network card that uses a MAC address. Here I've got another Ethernet network card, also uses MAC addresses. Ethernet uses MAC addresses. Each device in an Ethernet network is identified by its MAC address. The same is true on Wi-Fi. So the encapsulation or the way information is transmitted on the network depends on the link that's used, the physical media used. As an example again, this is a network interface card that supports fiber. So I can connect a fiber cable to the network card. Data is going to be transmitted across this cable using source and destination MAC addresses. That's how devices communicate on Ethernet. The same is going to be true for copper Ethernet, the Ethernet that you're probably very used to. So as an example, I could connect this copper cable to this network interface card. So again, just from a layer 1 point of view, obviously the implementation here is different. You are not going to use a fiber cable to try and connect to a copper Ethernet network interface card. That's not going to work. But from an Ethernet point of view, it looks the same. So if I captured traffic on the fiber cable and looked at the Ethernet frame, it would look the same on copper as well as fiber. Implementation is the same at layer 2, but at layer 1, it's different. Same is true for Wi-Fi. If I look at the destination and source MAC address on Wi-Fi, it looks the same. So if I'm looking at Wi-Fi and Ethernet, it's going to look very similar at the higher layers, but obviously at layer 1, it's very different. This is using air, this is using copper. The physical implementation is very different. But things change. For instance, when you go from Ethernet, this is an Ethernet port on this router, to something, and this is an old example, I'll show you some modern examples in a moment, a serial interface. So let's say my network interface card is in my PC and I've got it connected to this router. The traffic is going from the PC to the router through Ethernet, but when it goes across a serial link, serial links don't use MAC addresses, so the framing, the error correction, etc. is different on a serial link. So if I was sending traffic from a PC using Ethernet and it went across a serial link to another router, if I captured traffic on the serial interface, it would look different to the Ethernet interface. This is using Ethernet framing. The way that the frame looks, and I'll show you what that looks like in a moment when we use Packet Tracer, but the way it looks on Ethernet is going to be different to the way it looks on serial. Now, in the same way, here's a router with some Ethernet ports. If I connected my PC to Ethernet on the router, traffic that's sent across here is Ethernet, but in this example, might go across 4G. So the layer 2 implementation is going to be different across 4G versus Ethernet versus an old implementation like a serial interface. Wi-Fi and physical Ethernet look very similar, but if you looked at the encapsulation, in other words, what the frame looks like at layer 2 here, it would look very different to Ethernet. Now, that word frame I'm using on purpose because when we look at the traffic on a network, we will talk about bits at layer 1. Because it's binary bits, zeros and ones transmitted via light or electrical signals or something else. We talk about frames at layer 2. I'll show you once again what a frame looks like in a moment, but we talk about frames at layer 2. At layer 3, we talk about packets. So a router sends packets at layer 3. And then at layer 4, we talk about segments. Now, there's a lot of information here. I'm going to repeat myself, so don't worry if it's a bit overwhelming. The point is that different devices reside at different layers of the OSI model, such as a switch at layer 2. The traffic sent at layer 2 is a frame, and layer 2 looks at the physical addressing, which could be MAC addresses on Ethernet and on Wi-Fi, looks at framing and error correction between directly connected devices. Now, again, the reason we say directly connected is if we look at Ethernet here, it's between this network card and the router. But when the router routes from one media to a different type of media, such as serial, the communication here is between this router and, say, the other router connected on the other side of the cable. It's got nothing to do with what this PC is sending on the network. In the same way, if you send traffic through Wi-Fi to your Starlink, that's communication between you and Starlink across, say, Wi-Fi. Or could be physical Ethernet. So I could plug Ethernet in here. Different type of communication between the routers communicating through the satellite networks versus you using Wi-Fi on Starlink. Forgive my bad drawings now, but let's assume that you've got a PC. So here's my PC. It's sending traffic via Ethernet to a router. So this is Ethernet encapsulation used here. So as an example, it might be Ethernet 2. When it goes from the router to another router, this could be a serial link. And on this link here, we use MAC addresses, but on a serial link, there are no MAC addresses. The encapsulation used here is Ethernet 2 in a lot of cases, but the encapsulation here could be PPP. So notice it changes every hop between routers. The PC on this side could be using Wi-Fi. So I'll just draw Wi-Fi like that. Notice Wi-Fi is different to serial, which is different to Ethernet. Every hop, this changes. You're not going to use PPP on your Wi-Fi link. Every link uses a different encapsulation. So at layer 2, this changes every time we go through a router. The router actually strips the layer 2 information and recreates it when it sends the traffic from one interface to another. But IP, version 4 as an example, at layer 3 is end-to-end. So when you communicate through IP, you're communicating from one device to another like this. It's end-to-end. Now, you'll learn about NAT and how we can change IP addresses, but essentially, for the moment, think of it as follows. You are sending traffic from this PC to this PC. IP addresses are used for end-to-end communication, routing across multiple links. Layer 2 is used on a per-link basis. So at layer 3, or the network layer, we are providing logical addressing, which determines the best path through the network. At layer 1, we have physical addressing. Again, on a network interface card, the manufacturer burns in the MAC address or media address for the device. You can often change that, but notice it's burnt into the network card. When you buy a network card, it has a burnt-in address, so a MAC address associated with the card that you could perhaps change, but it has a hardware address identifying this device on the network. IP addresses are logical addresses. Those are addresses that we as an administrator would configure. You can change your IP address. Think about it. When you connect to one Wi-Fi network, it may use a specific IP address. When you connect to a different Wi-Fi network, it may use another IP address. So in this example, I'm connected to a specific Wi-Fi network. I'm just going to hide my Wi-Fi networks to keep that private. But notice I have a MAC address and an IP address. IP address was automatically allocated. IP address at the moment is 192.168.0.155. I have my subnet mask and my default gateway or router. So address was allocated automatically or through dynamic host configuration protocol or DHCP. I have a specific IP address. If I jump to a different Wi-Fi network, the IP address has now changed. It's 192.168.132. Different IP address, different default gateway. Now, MAC addresses don't normally change unless you specify an option here like private Wi-Fi address. They say here using a private address helps reduce tracking of your phone across different Wi-Fi networks. If you use the same MAC address the whole time, which is the burnt-in MAC address, your phone can be tracked. So to help stop tracking of your device as it moves from one network to another, what Apple is doing here is automatically changing the MAC address when you move from one Wi-Fi network to another. So again, the phone has a burnt-in MAC address that's used to connect to the Wi-Fi network. Same as here. You could change this MAC address, but by default, it'll just use a specific MAC address to identify that device on the network. IP addresses will change and can be changed to allow for routing through a network. And we're going to spend a lot of time looking at this. What we're going to do is configure routers. So forgive my drawings, that's supposed to be a router, which will have a link, say, to another router, which will have a link to another router, and say a router on this side. To get from router 1 to router 2, what's the best path? Let's assume that this link is 100 megabits per second, and this is only 1 megabits per second. It's going to make sense to send it across two 100 megabits per second links rather than, say, 1 and 2 megabits per second link. So you, through IP addressing, as well as running routing protocols, can say, okay, to get from this network to this network, I'm going to route this way. And IP addressing allows you to configure a specific subnet, as it's called, or network per interface. So every link or every network that you connect to will have a subnet. Again, look at your home network. So have a look on your own device. Here I have a network of 192.168.1.0. I'll talk about subnetting in another video, so don't worry too much about that. But notice the first three numbers are 192.168.1, which equates to the 255.255.255 in the subnet mask. Again, don't worry too much about that if you're not sure. I'll talk about subnetting in more detail later, but the idea is we have a logical addressing that allows us to route from one network to another. On this network, and I've just jumped now, subnet mask is the same. Notice the network is 192.168.0 now. The 255 there is indicating which is the network address. So the network address here is 192.168.0. The previous one was 192.168.1. So they are different networks, different subnets as we call it, allows us to route traffic from one network to another. And you'll learn a lot about that in this course. But the idea is that we have a logical addressing. You can change your network addressing very easily in your home network. You could set it to something else. You might not want to use what your router at home has set up by default. So this little TP-Link router might be using 192.168.1.0 as the network, and you could change that. It's a logical address. We often don't change our MAC addresses because they're burnt in. But as you saw in the Apple example, Apple is changing the MAC address when you go from one network to another for privacy reasons. Okay, next layer, transport layer. So what is the transport layer about? It supports communication between end devices across a diverse network. The two big protocols used at layer 4 are TCP and UDP, Transmission Control Protocol and User Datagram Protocol. Think of the following with regards to TCP. TCP is like a phone call. It's going to make sure that the other person is there and make sure that they get the data. So when I call you and you answer, you typically say hello, and then I would say hello. So it's kind of like in TCP where we have what's called the three-way handshake. We are agreeing on certain things before we transmit data. If I want to tell you my telephone number as an example, so let's say my telephone number is 555-1234. I would say, my telephone number is 555, and you would say 555 to confirm that you got the information. Then I would say 1234, and you would confirm by saying 1234. So I'm telling you the information or the data, and then you are confirming it back or acknowledging the data. It's a connection-orientated protocol and make sure that the other party gets the data. So Transmission Control Protocol is connection-orientated. We set up a connection. So I phone you, you answer the call. We acknowledge that by saying, hello, how are you? And we have sort of a conversation first, and then I transmit the data to you, and you confirm that you got the data or you acknowledge that you got the data. User Datagram Protocol, UDP, is not like that. It just sends the data and says, good luck. So send it. I'm not going to confirm that you got it. Hopefully you did, but I don't know if you got it. So that's kind of like writing an old-fashioned letter. So I write a letter, put it in an envelope, and I post it. I don't know if you got it. Maybe you got it, maybe you didn't. Who knows? Hopefully you did, but I have no confirmation that you got the data or the information. Whereas with TCP, you are confirming that you got every part of the information. Now, layer 7 or application layer, or if you want to be precise, 5 to 7, represents data users, encodes, and controls the dialogue. The whole idea here is that we are setting up, for instance, a session between an HTTP client and an HTTP server. So the client and the server are agreeing on certain parameters. And again, we'll cover that in a lot more detail as we go through the course. You've interacted with applications all the time. So you're using a web browser as an example. That's the most common type of application that we use today, but it doesn't have to be. Other applications use protocols such as FTP or TFTP or SSH or Telnet. Various applications use various protocols for communication at layer 7. Some of those applications make sure that the data doesn't get lost. However, when we use voice, so we're making a voice over IP call, it doesn't make sense to retransmit data that's lost. So if it's lost, it's lost. We don't make sure that the data arrives successfully. So voice protocols simply send the traffic across the network and don't make sure that the other party got it. Now, again, there's a lot of information here. We are going to spend a lot of time going through this information in the course, so don't worry too much about it. If you're struggling, what I want you to understand for the moment is that at layer 1, it's about bits. We are sending bits of data. At layer 2, we've got MAC addresses. At layer 3, we've got logical IP addresses. At layer 4, we've got TCP or UDP. And at layer 7 or 5 to 7, we have got applications such as HTTP, FTP, etc. So again, layer 1, we have Ethernet or Wi-Fi. It doesn't have to be those two implementations. Again, serial is a different type of implementation. We've got 5G, various types of implementations at layer 1. At layer 2, we've got encapsulations such as Ethernet 2, the most common type of Ethernet that you'll encounter. But on a serial link like this, you might have had point-to-point protocol or PPP or HDLC. Different types of encapsulations are used on different type of media. Fortunately, today, it's much easier. We're going to focus on Ethernet. When I started, we had to learn all kinds of implementations, ATM, HDLC, PPP, and a whole bunch of others, which I won't bore you with. Today, it's easy. Focus on Ethernet. At layer 3, we have IP version 4, IP version 6. Again, different protocols were available at those layers. You don't have to run IP version 4 or IP version 6. In the old days, we had a protocol called IPX SPX. So that was similar in concept to TCP IP. A whole bunch of other protocols existed. NetBEUI is another protocol that existed, and you'll find that in old versions of Windows as an example, but not in modern versions of Windows. In the real world today, we are focusing, fortunately, on TCP IP, because remember, it's the TCP IP model that won. The OSI model didn't win. TCP IP is what we use today. That's what won. So we use TCP or UDP at this layer. And at layers 5 to 7, we're using HTTPS, Telnet, FTP, TFTP, etc. Lots of protocols exist here. So those are just a sample of them.